Ready for a deep dive into one of the universe's biggest mysteries? We're tackling dark matter today.
Really puts the dark in deep dive, doesn't it?
You got that right. We've gotten a few requests to unpack this topic, and honestly, it's one of those things that can make even space enthusiasts scratch their heads a little.
Yeah, it's not exactly intuitive, this idea of something invisible making up a huge chunk of, well, everything.
Exactly. So let's dig into this lecture we got, shall we? We'll start simple, what is dark matter, and then try to get a grip on how scientists are trying to find something they can't even see.
And the first thing to wrap our heads around is just how much of the universe is supposedly made of this stuff. We're talking a whole lot more than what we can see.
Yeah, the lecture mentioned something about only 5% of the universe being, well, the stuff we're familiar with. Planets, stars, cosmic dust bunnies, the works.
It's wild, right? It's like we're only seeing the tip of a cosmic iceberg. The vast majority, like 95%, is this hidden realm of dark matter and its equally mysterious cousin, dark energy.
Okay, wait a minute. So we're basically trying to understand the universe when 95% of it is playing hide and seek. Talk about a challenge.
Right. It's like walking into a room and only seeing a few objects here and there, but you can feel that there's a lot more stuff you just can't see.
And to make it even more interesting, it's not like we can just turn the lights on and suddenly see everything, right?
Exactly. We're forced to be clever. Luckily, this hidden stuff does leave some clues, like gravity, for instance. We might not be able to see dark matter directly, but we know it's got to be there because it exerts a gravitational pull.
Ah, so it's like trying to figure out what's in a wrapped gift just by shaking it. We can't see inside, but we can feel the weight and maybe hear things rattle around.
That's a great analogy. And speaking of shaking things up, one of the first people to really start poking at this mystery was an astronomer named Fritz Zwicky back in the 1930s. He was, shall we say, a bit of a character.
Oh, how so?
Let's just say he wasn't afraid to speak his mind, even if it ruffled some feathers. But brilliance often comes with a bit of eccentricity, right?
So what was Wicky's big contribution to this whole dark matter puzzle?
Well, he was studying a group of galaxies, and he noticed something really strange. They were moving way faster than they should have been, based on the amount of visible matter alone, like seriously speeding.
So what was holding these galaxies together? Why weren't they just flying apart?
Exactly. And that's when Zwicky had this groundbreaking, if somewhat unsettling, thought. There had to be a lot more mass out there than we could see, providing the extra gravitational oomph to keep these galaxy clusters from scattering. He called this unseen stuff Dunkelmaterie, German, for, you guessed it, dark matter.
So that's how it all started, with Zwicky shaking things up literally and figuratively.
Pretty much. He was definitely onto something big, even if it took a while for the idea to really gain traction. I mean, it's not every day that you propose the existence of something invisible that dominates the universe.
That's for sure. Makes you wonder, though, what other groundbreaking ideas might be floating around out there just waiting for their moment. But we're getting ahead of ourselves. The lecture also mentions someone named Vera Rubin, right? What was her role in unraveling this cosmic mystery?
Right. So Vera Rubin's work, a few decades after Zwicky, really solidified the case for dark matter. She was studying how stars move within galaxies specifically, their orbital speed at different distances from the center.
So like planets in our solar system, you'd expect stars farther out to be moving slower. Takes longer to complete an orbit if you're on the outer lanes of the cosmic highway.
Exactly. That's what you'd expect based on good old Newtonian physics. The farther out you go, the weaker the gravitational pull, the slower things should move.
But that's not what Rubin observed, is it?
Not even close. She found that stars on the outskirts of galaxies were moving way faster than they should based on the visible matter alone. It's like they were thumbing their noses at the laws of gravity.
So either these stars missed the memo on how gravity's supposed to work, or something else was going on.
Yeah, rebellious stars didn't quite cut it as a scientific explanation.
Rightfully so. So what was the alternative?
Well, the most plausible explanation was that there was a lot more mass in these galaxies than met the eye. Mass we couldn't see, but that was exerting a powerful gravitational influence. That's where the idea of dark matter halos comes in.
Dark matter, halos.
Imagine this. Each galaxy nestled inside this giant invisible halo of dark matter. You can't see it directly, but it surrounds the galaxy, extending far beyond the visible stars.
And this invisible halo is what's providing the extra gravitational muscle to keep those speeding stars from, well, taking off into the cosmic void.
Exactly. Think of it like a cosmic spider web. The web itself, that's the dark matter, invisible but vast, and the glittering galaxies we see are like dewdrops clinging to its strands.
Wow, that's an amazing image. So we've gone from Zwicky's, hey, something's fishy with these galaxy speeds, to Rubin's observations that really solidified this idea. Hold on, there's a whole lot of invisible stuff out there calling the shots.
And by calling the shots, we mean shaping the structure and evolution of galaxies, even the universe as a whole. It's like realizing that the universe's instruction manual was missing a few crucial pages.
Talk about a plot twist. And this is where things get even more mind-boggling. Because then the question becomes, what is this invisible stuff made of? The lecture dove into some of the contenders, right?
Right. And the most straightforward thought, maybe a bit too straightforward, was that dark matter was just regular matter, the stuff we're made of that was really good at hiding.
Like, it wasn't emitting light, so we couldn't see it.
Exactly. Astronomers have a fancy term for this regular matter, by the way, baryonic matter.
Baryonic matter, got it. So protons, neutrons, the stuff of periodic table fame just lurking in the shadows.
Essentially. The problem is, if dark matter were made of this ordinary baryonic matter, even if it wasn't shining bright, we'd still expect to see its effects in other ways.
Like what? Give me an example.
Okay, so it should interact with light, even if it doesn't produce its own. We'd see more gravitational lensing, for example.
We'll get to lensing in a bit, right?
We will. But just to say, we're not seeing enough of these telltale signs to account for all the dark matter we know must be lurking out there.
So if it's not just regular matter hiding in plain sight, then what else could it be?
That's the million-dollar question. And it's led physicists down some seriously fascinating rabbit holes. The lecture mentioned WIMPs, for instance.
WIMPs. Okay, that sounds like something straight out of a comic book.
They're definitely one of the more popular suspects in the lineup. WIMPs stand for weakly interacting massive particles.
Catchy. So what makes a WIMP a WIMP?
Well, they're these hypothetical particles that have mass, so they gravitate, but they interact very, very weakly with normal matter and light.
So weakly interacting, meaning like a WIMP could pass through a planet, a star, even a whole galaxy, and barely notice.
Pretty much. Imagine a WIMP flying through a light year of lead. It's got a better chance of winning the cosmic lottery than interacting with even a single atom.
Wow, talk about a needle in a cosmic haystack.
Yeah.
So if they're that elusive, how do we even begin to search for them?
Well, remember that cosmic spiderweb analogy we talked about? Turns out that can actually help. One technique is called gravitational lensing.
Right, we touched on that earlier. Something about warped space-time acting like a cosmic funhouse mirror.
Precisely. Imagine light from a distant galaxy traveling towards us. If it passes by a really massive object, like a cluster of galaxies chock full of dark matter, the light gets bent.
So we see a distorted image of that galaxy. How does that help us find something invisible?
It's all about the amount of distortion. The more distorted the image, the more mass must be there, bending the light. We might not see the dark matter directly, but we see its gravitational footprint.
Okay, that's pretty clever. Seeing a footprint in the sand,
Yeah.
Someone was there, even if you didn't see them make it.
Exactly. It's one of the ways we can map out the distribution of dark matter, even if we can't see the stuff itself.
Amazing. Any other tools in our cosmic detective kit?
Well, there's another incredible clue hiding in plain sight, something called the cosmic microwave background, or CMB for short.
CMB. Oh. It's like the oldest light in the universe, right? Leftover radiation from the Big Bang.
You got it. It's often called the afterglow of the Big Bang, this faint radiation that's been traveling through the universe for almost 14 billion years.
So how does this ancient light help us with something as mysterious as dark matter?
Think of it like this. The CMB is like a baby picture of the universe, taken when it was just a few 100,000 years old. And just like a baby picture can tell you a lot about a person's family history, the CMB can reveal clues about the early universe, including how much dark matter was hanging around back then.
Okay, I'm following so far. So what's the verdict? What does the CMB tell us about the universe's dark side?
It screams dark matter. By studying the patterns in the CMB, scientists have figured out that dark matter makes up a whopping 85% of the total mass of the universe.
85%.
It's a lot.
It really drives home the point that what we see, all the stars and galaxies, it's just the tip of the cosmic iceberg.
Exactly. We're really dealing with a universe we barely understand, dominated by this invisible stuff.
Mind-blowing. But knowing it's there is one thing. Actually detecting a dark matter particle, that's a whole different ballgame.
Yeah.
The lecture mentioned those deep underground detectors. How do those work exactly?
Ah, yes. These detectors are incredible feats of engineering and patience, all rolled into one. Imagine a giant tank, like really huge, filled with liquid xenon.
Xenon, as in the noble gas. Why xenon?
It has to do with how xenon atoms interact, or rather, don't interact easily with other particles, makes it good at spotting anomalies. Anyway, these tanks are buried deep, deep underground, like in old mine shafts, to block out any stray particles that could mess with the experiment.
Right, kind of like needing a really, really quiet room if you're trying to eavesdrop on a whisper.
Exactly. And the idea is if a dark matter particle happens to collide with a xenon atom, it'll produce a tiny flash of light, a signal that these super sensitive detectors can pick up.
So they're waiting for dark matter to, what, bump into something and give itself away?
That's the gist of it. It's a long shot for sure, but if it works, it could be our first direct detection of a dark matter particle.
That would be huge. Now, what about the Large Hadron Collider? The lecture mentioned that as well. How does smashing protons together at crazy speeds help us find dark matter?
Good question. So the LHC wasn't actually designed to find dark matter, but there's a chance it could be created as a byproduct of these high energy collisions.
So it's like accidentally discovering a new recipe while you're trying to cook something completely different.
Something like that. If dark matter particles are produced, they'd be very hard to detect directly. But physicists are looking for telltale signs like missing energy and momentum that could hint at their presence.
Okay, so we've got underground bunkers filled with liquid xenon and giant particle accelerators smashing atoms together. It's amazing how far we've come from just noticing those weird galaxy rotations.
It's a testament to human curiosity and our drive to understand even the most mind-bending aspects of the universe.
Couldn't agree more. We've gone from, something's off with these galaxies to, hold on, the universe is dominated by something we can't even see. And the search for dark matter, it really highlights how much we still don't know.
It's humbling in a way, isn't it? Realizing how much is still out there, waiting to be discovered.
Absolutely. And who knows what incredible breakthroughs await us just around the corner. Maybe someday we'll be having a deep dive into the mysteries of whatever comes after dark matter.
Now that's a deep dive I'd sign up for.
This has been a fascinating exploration, but for now, we'll have to leave it there. We've covered a lot of ground, from those early hints of dark matter to the cutting-edge experiments searching for answers. It's a topic that really makes you think what else is out there, hidden in the shadows, just waiting to be found. Something to ponder until our next deep dive.